Okay, so here we are in my backyard to start out chapter 7. So it looks a little weird. Why are we in my backyard? And 2, why are we here at night? Okay, so we're going to have a little demonstration towards the end of the opening lecture here about something called effective nuclear charge. So this is a very important topic. It's essentially what positive charge is felt by an electron in an atom. So for this demonstration, we're going to use my light here to represent the nucleus of the atom. So however bright a particular light is going to tell us sort of the more positive of the charge that we're going to feel. So if we're seeing the full light, that means we're experiencing, say, the full positive charge of the nucleus of the atom. But if I'm able to block some of that, that means we're not feeling quite all of that nuclear charge of the atom. Okay, so we're going to do a couple of demonstrations on what this looks like. So to start, let's take a look at some definitions of what nuclear charge is and some diagrams about kind of what that looks like in an atom. Okay, so if we now flip down here, we are going to look at effective nuclear charge. Okay, so by definition, the effective nuclear charge is the positive charge felt by an electron in an atom. Okay, so if we're this electron right out here, it's how positive of a charge we feel. So I drew 1, 2, 3, 4 little pluses in here. So if we're an electron out here with a -1 charge, do we really feel a +4 sort of total positive charge from the nucleus of the atom? And the answer to this is no, not really. We don't. The energy holding that electron in is given by this formula here that we talked about in chapter 5. So the energy is proportional to Q1, Q2, where that's the charge of your positive particle and the charge of your negative particle divided by the distance. So as we move further away from the nucleus, or D gets larger, the energy required to hold that electron to that atom is going to decrease. And as the charges, so Q2 is always the same, it's always just the charge of the electron, but Q1 we're going to see does change depending on which electron you are in an atom. If you're one very close to the nucleus, this Q1 is going to be quite large. But if you're far away, like this one here, this Q1 is going to be a lot less. Okay, so let's put some other electrons in here and kind of take a look at what we mean. So what we are going to define is shielding or screening. So what that means is if you're an outer electron, that some of these inner electrons are able to block or screen this positive charge. So for example, this electron here is screened by 2. So these 2 electrons are taking away some of that positive charge. So the simplest way to think about it is 2 electrons can take away 2 magnitudes of the positive charge. So instead of feeling a +4, 1, 2, 3, 4, this electron is only feeling really like a +2 because this electron is canceling out a positive charge and this one's canceling out a positive charge. So this one is just feeling a +2. So what this is called is shielding. These electrons are blocking some of that positive charge from going through. So electrons can shield or cancel some of the positive charge felt by electrons sort of further away or in higher shells. So we have a relationship to talk about putting that stuff together, and that's Z effective, so ZF, or ZEF, or ZEFF. And ZEF is the effective nuclear charge. So again, it's that charge really felt by the electron due to electrons closer in screening. So to calculate that, we're going to have the atomic number Z. So remember, atomic number is just the number of protons in the nucleus. And from that, so that would be like the full positive charge, like for a carbon, like a +6. And S is what's called a screening constant. So that's essentially what factor of that positive charge is being blocked or shielded. Okay, so our shielding. Okay, so as we work through this chapter, we're going to see, number one, most of the screening is done due to electrons in lower n values. Okay, so this electron was kind of in this drawing like in n equals 3. So it's being screened by n equals 1 and n equals 2 quite effectively. But we're also going to see that you can have screening if you're in the same shell as well. So we do get a small effect from electrons in the same shell. Okay, so we're going to look for our demonstration at 4 examples. So I have them kind of drawn out here. So the first one is hydrogen. So hydrogen has 1 electron and n equals 1. Next, we're going to look at carbon. So carbon has an electron and n equals 2. Next, we're going to look at something like tin. So tin has its outermost electron and n equals 5. And then uranium. Uranium is going all the way out to n equals 7. Okay, so to do this, we're going to go back to my light bulb and we're going to do some screening of that positive charge. Okay, so let me get my screening. Okay, so our first example was hydrogen. So if I'm an electron here in hydrogen, I'm not experiencing much screening or any screening because there is no electrons that are able to get in the way and block some of that positive charge. So I'm feeling the full force of that positive charge on this electron here. Okay, our second example was carbon. So carbon are the outermost electrons are in n equals 2. So we have lower shell electrons or n equals 1 that are able to block it. So if you're a carbon atom, the screening would look something like this. Okay, still a whole lot of light coming through because there's not very many electrons that are able to actually block out that positive charge. So the light is less, but it's not much because there weren't a whole lot of electrons there to screen. Okay, our next example would be something like tin. So tin, we have our outermost electron in that 5th shell. So then we have the 4th, 3rd, 2nd, and 1st that are able to screen. So we would see something like this. So we have a lot more light being blocked by those, or light in this case is positive charge, being blocked or screened by those inner shell electrons. So the positive charge felt by those electrons is much, much less. Okay, our final example was uranium. So uranium with the 92 electrons, and we've got like 80 something of them are able to effectively screen. We're going to get something like this. Okay, so if you look really closely, you can see a little bit of light coming through. So we're not feeling a full plus 92. We're feeling something much, much less than that. Okay, so the light looks very, very dim coming through. So the screening here would be quite large. A lot of that positive charge is being blocked in this case. So S would be large. For our example for tin, okay, so tin would be kind of intermediate. A fair amount of light or positive charge is being blocked by those inner shell electrons. And then our screening for something like carbon is going to be very, very small because there's not a whole lot of electrons there to block. And then again, for hydrogen with the 1 electron, nothing really there to screen. Okay, so going to our drawing here, back to our drawing. So this is, again, the representation of kind of what we did up there with the screening. So hydrogen, the full light bulb or the full positive charge. For our carbon, again, with that transparency, a little bit of the light or the positive charge was blocked. For tin, with a lot of shells in here, that was like our white paper where it was starting to really kind of block that light pretty well. And then finally for uranium, with all of these shells here of electrons able to screen, we saw very little light. Or again, that represents our positive charge coming through. So again, this isn't feeling a plus 92. This is feeling something much, much less. Okay, so as we work through this chapter, we're going to actually be able to calculate what the screening constant will be using a couple of different methods. And we'll be able to calculate the effective nuclear charge different electrons in different atoms. Okay, and again, this is important because it's going to help us explain a lot of trends that we see in atoms. So it's going to help us explain sizes of atoms, and it's going to help us explain ionization energies of atoms. So very, very important topic for this chapter.